Alright guys, we're going to jump into our first couple sections of Chapter 11. Chapter 11 is going to be all about circles, okay? Not just circles, but lines that intersect circles, angles that are formed in relation to a circle, and then we'll finish up with circles on a coordinate plane when we learn about the equation of a circle. We can graph circles on an XY coordinate plane. But we first start with a couple lines that you'll see that intersect circles, and the first one we'll talk about are tangent lines, okay? A tangent line is a line in the plane of the circle that intersects a circle at exactly one point. Basically, it just barely touches the circle at one singular point. We've given you an example of that right here. This line here would be considered a tangent to the circle, okay, or a tangent line to the circle. Okay, they're kind of synonymous. A tangent line, okay? We also give you a quick definition of that point of tangency. So the point of tangency is where a circle and a tangent intersect. This, let's say we gave this an actual label of point A on this diagram. A would be the point of tangency, the point where the tangent line intersects the circle. Okay. One of the more important things that come from tangent lines intersecting a circle is what happens when we draw a radius to that tangent line. So we get a theorem. If a line is tangent to a circle, here would be your tangent line. Maybe we'll even label that with an L. So if a line is tangent to a circle, that would be L. Then the line is perpendicular to the radius drawn to the point of tangency. Okay? So what this means is if we draw a radius to the tangent line and it meets it at that point of tangency, right angles are formed. Pretty simple theorem. Basically, when a radius meets a tangent line at the point of tangency, right angles are formed. Just a little bit of a different way to think about, different perspective on that theorem. Okay, so that's one of the main theorems. The other one says that two segments tangent to a circle from the same point outside the circle have to be congruent. So basically, if you pick any point, in this case F, outside of this circle, and what you do is draw a tangent line kind of going to the bottom of the circle or the side of the circle, wherever this point happens to be. And you draw another tangent line, okay, two lines that meet only at one point on the circle. These two segments would be congruent. In this case, segment FG would be congruent to segment EF. And you're going to see problems here on our examples that deal with this. So let's turn the page. Two theorems that come from tangents being formed intersecting a circle. All right. Example 1. It says that ML and MN are tangent to circle O. Find the value of X. Okay. The way we want to attack this problem is to think of NOLM as a quadrilateral. This figure here, albeit made up of two tangent lines and two radii, it happens to be a four-sided figure. Okay, 4 minus 2 times 180 gives me 360 degrees total for the interior angles of this quadrilateral. Now you might be thinking, we're only given one angle, and we're looking for one angle. We know nothing about these other two, but we do. Based on the theorem we learned first, this is a tangent line. This is a radius meeting that tangent line at the point of tangency. We just learned a theorem that would say that that's a right angle. Same reason over here, this would be a right angle. And now these four angles would have to add up to 360 degrees total. So 117 plus 90 plus 90, that equals 297. 360 minus 297, x is going to equal 63 degrees. All right. So basically using the information we've been provided to help. Okay. That theorem gave us these two right angles. It allowed us to solve for x. Example 2, segment ED is tangent to circle O. Find the value of x. Well, right away, radius meeting a tangent line, we know that this is going to be a right angle. Let's see how that helps us. Oh, it helps us a lot. This is a triangle. The three angles of a triangle have to add up to 180 degrees. And x would be 52. All right, cool. Now you might see other problems once we get to our homework where something like this happens, but we've given you some lengths. Well, what this would allow us to do, once we know this is a right angle, that brings SOHCAHTOA into play. It also brings the Pythagorean Theorem into play. Okay, once we know we're dealing with a right triangle, we can do all those things if we're ever looking for some side lengths. Example 3, a belt fits tightly around two circular pulleys as shown in the diagram. Find the distance between the centers of the pulleys. This is a really, really interesting, kind of tough problem. Okay, so we put this on here as an example because it's interesting some of the things you can do in a situation like this. Okay, now it says find the distance between the centers of the pulleys. All right, so I'm going to just label that here. This is going to be x. Now, many students kind of just assume that x would be 35 inches, just like this, but it's not. Okay, if you can kind of visualize this, the centers of these two pulleys, okay, this point here and this point here, they're on kind of the same horizontal line. This line here is not horizontal. How would we know that? Well, if the centers are in the same place, this pulley is smaller than this one, so from the top of this pulley to the top of that pulley, there would have to be some sort of incline, okay, which means this length and this length would not be the same. So what do we do here? Well, there's kind of a trick to what we call a pulley problem. Okay, and the trick is, what we're going to do is draw an extra segment here. So I've got the length I need, okay, I've got this information, I know the radius of this, I know the radius of that, okay. We're going to draw an extra segment, and what it's going to do, this is kind of the trick. Draw a segment from one center to the other radius that creates a rectangle and a right triangle. And I'm going to show you how that works here. Okay. In theory, what we want to do is draw that extra segment from the smaller pulley's center to the longer pulley's or the larger pulley's radius. And what we're doing is we're going to draw a segment that's parallel to this one here. Okay? So I'm going to kind of just freehand this a little bit. It's not bad. That's the trick there. Now, if we draw a segment parallel to this one, and we know that these are already right angles, based on lots of different things we've already learned in geometry, that would make these right angles. You can think same side interior angles adding up to 180 if you want. All right. Which means that this is a rectangle. So we just created a rectangle. This is a right angle, meaning this has to be a right angle. Okay. Linear pair, this one's 90, this one has to be 90. What we've done is we drew a segment that created a rectangle and a right triangle. Now let's talk about rectangles. In rectangles, the opposite side lengths are congruent, meaning that this segment we drew was 35 inches, and it also means that this part of the radius would be 8. We've now basically broken up this radius into two parts. this length here and this little length here of our right triangle. Okay, take a look at your rectangle. 35, 35, 8, 8. You guys have known forever that that's what a rectangle looks like. Okay. Now, we don't really care about the rectangle anymore, but let's try to use that information to help us with our right triangle. Okay. If this radius is 14, and we already know that this part is 8, well then 14 minus 8 leaves this piece to be 6 inches. So that 14-inch long radius has now been separated into two pieces, one 8 inches, one 6 inches. And now we actually can solve for what we labeled x, the distance between the centers. What we have here is a right triangle where we have the two legs and we're looking for the hypotenuse. I just pulled this right triangle right out of our diagram. So, if we have two of the three sides, we can use the Pythagorean Theorem. So we've got 6 squared plus 35 squared. So we got 1225. We have 36 equals x squared. We get 1261 equals x squared. And we take the square root of 1261. And approximately 35.5 inches. There we go. I really like that problem. I think, you know, when traditionally, if we were in the physical classroom, we would kind of put some groups together where you guys attack this problem, and we see usually every year, you know, a handful of groups come up with, you know, this kind of creative way to solve this. And then, you know, we kind of put it all together, and a lot of students that are in groups where maybe they don't come up with something are like, oh, that was really cool. You know, drawing an extra segment that creates, you know, a rectangle and a right triangle, because, you know, the original shape, if we didn't draw this in here, we have this quadrilateral that we know very little about. We know that there's right angles here, but we don't know anything else. It's not something that we can work with. Okay, so you know, drawing extra or sketching extra things that allow us to create figures that we can work with is important. So that's going to be it for part 1 of these notes. Part 2 we'll talk about chords, but tangents, we should now be tangent experts.